For the last 15 years or so, I've been teaching a course at the University of Aarhus at the Computer Science Department called Embedded Systems Embodied Agents. The course is about programming robots in Java. And the robotic systems that we've chosen for this is the Lego Mindstorms NXT kit, robotic kit, that out of Lego bricks can be used to build different robots that can be controlled by the NXT control unit. In this talk, I'll talk about the course, the reasoning behind the course, the content of the course, and show you some examples of some of the end course projects that the students have been doing in this course. It's a one semester course, and it's divided in two parts in a 10-week session where each week we have lectures and lab sessions that take place in this room, the Lego room, Ole's playroom for kids. But to get funding, I need to call it the Lego lab. The other part of the course is an end course project. It's a 10-week period where the students in groups of 2 or 3 select their own projects and finish it and present it to me and hand in some lab notebooks describing their process and the product they have done. And this is how the lab looks at the end of the end course project period. And when I complain about it to my students, they always say, why don't you build a robot to clean up? The Lego Mindstorms kit is a bunch of Lego bricks and then some elements that can be used to build Lego robots, like this one. It's rather easy to build these. You build them out of Lego bricks and then you add on the little controller here, add on a sensor and add on 2 motors in this case to have a fixed and ready Lego car to run around. At the core of this is the NXT. It's the control unit. It's powered by a rechargeable battery, which is very practical when you have 30 or 50 students. There are input ports for different sensors and output ports for actuators, motors and lamps, etc. For programming, we use the LeJOS system. It's a very active environment, open source environment. The latest version is from February this year. It started out with the earlier robot control unit from Lego, and now they have also developed it for the new, that's 3 or 4 years old. And it's a complete Java system with API for this box and an API for the PC. So it's rather easy to write a couple of programs, one for the PC and one for the robot, and make them communicate by means of Bluetooth or USB. So you have a whole system consisting of programs on PCs and programs on these NXTs. They also have a very nice tutorial, which is important when you want to teach. The architecture of the LeJOS system is described here. The yellow part is the firmware that you download once and for all in the flash memory of the processor inside the NXT. Then the user program can use the native methods that give you access to the motors and sensors and Bluetooth, etc. But you can also use some of the classes from the API, for instance, a rather high-level navigation class that can make you navigate your robot around in the room so you know where it is. The very low level, there's another processor inside here, but you don't have to care about that. There are two processors in here to make sure that the real-time requirements are dealt with. First of all, the students need to learn about the Java API that's running on the NXT. And for almost every device, the buttons, the screen, etc., there's a class in the API. And in this case, it can both be used, the LCD display can be used both for text and graphics. For instance, it's rather easy just to describe for debugging purposes values out on the little display, or you can also use it for graphic output. During the first 10-week period, I organized the course in some lectures where this week, the second week, talk about PID controllers, and I'll come back to that. And furthermore, I described the embedded Java. So the first part of the course is about embedded systems. What is an embedded system? How do we write programs for it? What are sensors? What are actuators? And we use the NXT and the robots that we can build with it to describe both the embedded Java and controllers. For teaching about controllers, I use a chapter of this book, one of the pioneers of using robots in hands-on education. This is an introduction to engineering for MIT students. And back in the early 90s, he designed a robot with Lego bricks, Lego wheels, Lego motors, but with some homemade electronics on board to run interactive C programs on board of these robots. Now, remember that it's computer science students I'm teaching. They know nothing about control systems. They know nothing about regulation. So I need to start from the beginning by describing what is an embedded system that has one control loop. For instance, this little car following a wall, getting feedback from sensors measuring the distance to the wall and using motors to drive either towards or away from the wall. So two wheels are used as actuators. A bend sensor tells how close to the wall the little robot is, and then we need to write some control loop that every now and then looks into the environment and try to refine or adjust the position with regard to the wall. And in this book, it's explained rather nice what a simple control loop is with on-off control or bang-bang control. If it's too close to the wall, drive right to get away from the wall, or if it's too far away from the wall, drive left. And it's the value of the bend sensors that is interpreted as being too far away or too close to the wall. Okay. The first week, I introduced this idea by means of a lab session where they built this robot, or this little Lego car. Add a light sensor, download a line follower program, and this is their first embedded Java program. So they need to know how to use the classes that are accessible in the API so that we can access the light sensor. In this case, we have an instance of the light sensor class with a constructor parameter saying that it's connected to port 3. Then we turn on the floodlight, the red light, so it's reflection from red light from the surface that we get. We can read the value when we have this instance, a value between 0 and 100, 100 being very bright, 0 being black. And we can use it for testing whether we are on the black or on the white surface. At least if the robot is on a surface like this. The motors are accessed similarly through APIs. Motor port B and C are used in this case, and the method control motor with 2 parameters, a direction, forward, backward, stop, etc., and some power, a number between 0 and 100, and in this case it's a pulse width modulated 9 volt power supply to the motor to supply different power levels to the motor. And then the control loop is very similar to the loop from Fred Martin's book, just this simple on-off, bang bang. If we are on the black, on white, turn right. If we are on black, turn left. And I have calibrated this little car to the lighting conditions in here. And here you see how this control loop will make it follow the line. One of the things that I say at this point is, from the outside, we will describe this as follow a line or follow an edge. But there's no representation inside the program of a line. It's just 2 simple rules, turn left, turn right. This is how you get back from the city one late night, Saturday night, following a wall or turning left, turning right. Okay. One of the parameters that they are supposed to investigate is, for instance, the threshold, and furthermore, the sample rate. This is very new to computer science students, that the sample rate you use in an embedded systems determine how good this embedded system is. One of the next small lab sessions to get them to know about controllers is to build this little robot. So now you can see the advantage of having Lego robots as the kit that we use for robot programming, because we can rebuild and rebuild for each lab session whatever we like. Investigate large wheels, small wheels, whatever. Just like the Segway, we're trying with this one to balance on 2 wheels. And we use the light sensor to measure the distance to the surface, and hence also how much it's away from the upright position, whether it's bending forward or bending back. And from this book on Lego Java programming with the leJOS, I've stolen this little PID controller. So this PID controller will try to balance a legway like this one. Yeah.
What's a PID?
I'll describe that now.
Yeah.
You're in computer science. Yeah. Because if we try with the simple on-off control, bending like this, drive like this, bending like this, drive like this, then it will fall over immediately. I mean, you can't use this strategy for controlling when it's balancing. Okay? And the reason is that it's falling too fast. A PID controller has 3 terms: proportional, integral, and derivative. Proportional means that we somehow measure the error how far away are we from the upright position that we want. This is the offset. Then we read the light sensor value and subtract that from the value that we wanted to have, because that's the right distance. And the error is then calculated and used for calculating how much should we drive forward or backward. If we only use the proportional term, we take this error and multiply it by some constant and put it into driving forward or backward down here with the motors. So proportional to the error, we try to adjust the speed in one or the other direction. But if it's upright, then the proportional term is 0. If we only do that, it will fall over very quickly, because when it passes through the position that we want, it has too much speed. So, okay. Then we take the derivative, which is the speed. In this case, the difference between the previous error and the error, the actual error. This is the D term. By putting that in, it'll stop a little before the position that we want, just like an elevator. It approaches the floor and stops and settles down. It's not just like in Tivoli's, then it's more fun to have other constants, right? But in this case, we want it to stop gently at the upright position. And the integral term is not that important in this case, but normally with the elevator, it makes sure that we get just right at the position. We integrate the error, and when the integral is large enough, we give it a little push. Now the problem here is to find out what should these constants be? And what is this strange term? And why do we have this? This is what they investigate during this course, during this lab session. Furthermore, they learn how to debug embedded systems by having a GUI running on the PC with typing in new constants, sending them to the program while it's running, and then getting new constants into the PID controller. I can demonstrate how a PID controller works in this case. You saw how it oscillates around the edge. But if I just use the P term and the D term in this case, and calculate the error with respect to just above the edge of the light sensor, then it will drive like this. That's more normal. It's a driverless car trying to get around. Right? And you can see if I put it here, it'll just correct each time it. Oh, it's. This is where the debugging tool comes into handy, right? In the mid, or almost in the end of the 5-6 weeks, we have a competition where the students are supposed to build a robot of their own choice. It should start at the floor, try to get up here, turn around, and go back again. Now, this is really engineering. Mechanical design, instrumentation, choosing the sensors to get the information they need, but also trying to get to the point where they can choose a strategy for running up and down this Alishan train track. It looks as if they should follow the line, and one of the groups actually did that. With 2 sensors driving rather quickly, but only using the line every now and then. So there are stages in this program, whoa. There are stages in this program where it knows that now it's on this slope or on this slope, because now it should catch up the line on the left or on the right. And they were supposed to run as fast as possible from the green area to the green and back to the green area. And here you can see the time, or you can't see it, but they handed in the time to me, and I trusted them. But there were some other strategies, like this one. It's coming out of the dark. There's no sensors. It's plain, hand-coded, timed motor commands. And you can see it's late night. They've been working on this the whole day and the whole night. And every now and then they just corrected it a little and the battery level, but now see what they do. So instead of driving all the way back here, they carefully throw themselves over the cliff and down in the green area. Here it's nice to have Lego. Right? And this is a very risky and very non-robust solution, but I mean, in this case, it worked. Fortunately to me, because I don't like this kind of solution, fortunately to me, it was took a little longer time than the other solution. And the prize was a dinner in town on me, so the first team got a dinner in town. So the first part of the course will teach them that an embedded system has some stimuli from the outside world going through the sensors into the control program. And here they learn about sensors. When they come, they have this misconception that sensors measure information out there in the real world. They are unambiguous and without noise. And they learn totally different issues like noise and very ambiguous numbers that come. Furthermore, when it comes to the actuators, motors are not similar, not from Lego, and you have to program this into your control program. So it's not an ideal world, it's a very real world that their robot is supposed to live in. It has 3 components. Each of these components independently determine the behavior of the robot. The environment, the physics of the robot, the wheels, the placement of the wheels, etc. And then the control program. For computer science students, it comes as a surprise that the control program is not enough. I mean, they come and say, we can prove it. No, you can't, because there's an environment and there's physics of the robot. Then the embodied agent part. Autonomous agents are robots that can behave autonomously, deciding on their own what to do. And adaptive is robots that can adapt to the environment. If you saw the competition arena, you saw that the lighting conditions were very different on the slopes, the 2 slopes. And they didn't realize that until very, very late during their competition. You have to adapt to the lighting condition in the environment. When you talk about agents, you talk about systems that have goals. This is very hard for technicians to understand. We have a coffee machine in the lab. It was put there by Studenterfonden, a local organization for earning money from taking coffee or selling coffee to the students. Some of the students found out that they could hack the machine to get free coffee by some strange push of the buttons, right? It took 2 years before the organization realized that there were no money coming in. They were filling powder into this machinery every week. Now the guys who had programmed this coffee machine didn't think of the goal of this machinery. The goal is not to give money out, is not to give coffee out. The goal is to earn money for its owner. So the first component to build into such a system is a little component that sends SMS messages to its owner when no money comes in. Then the rest with the coffee and all that, that's okay. But this is the most important part of the system to make sure that the goal is reached. The difference between embedded systems and embodied agents can be described very easily by taking an industrial robot and the robot baby seal Paro. This is supposed to exist in a very engineered environment with very engineered actuators and sensors and a sequential strategy built into its program. A single plan for doing its job. This is an embedded system living in a strange environment, in hospitals, in nursery homes, being taken into bath, being hugged, being handled in every possible way. To make sure that this will work in any environment, we need to program it differently. Fred Martin has called this a reactive strategy, to look into the conditions of the environment by means of the sensors and choose some action depending on what's going on in the environment. So if somebody is hugging Paro very hard, it will scream out loud. And if somebody touches it gently, it will say sounds and behave so that the owner will know this is what I want. And it also learns its own name. These reactive systems built into systems that were supposed to live in environments that we do not know in advance started to be built in the 1990s. Rodney Brooks, also from MIT, coined the term a subsumption architecture. 3 different behaviors are running on one robot as independent threads. Each of them can behave and make the robot behave running alone on the robot. For instance, a random drive is just a thread that uses the motor to randomly drive around. This one has input from some sensors that register if there's something in front of the robot and then use the motors to get away and avoid. This one up here, every randomly time interval decide to dance and play some tune. How do these 3 behaviors or behavior modules exist together and share the same motors? In Rodney Brooks' case, it was based on static priorities. If this one is running and the others are passive, that's okay, get through. But if this one wants to control the motors, it suppresses this one's access to the motors. So we have priority with respect to access to the motors. And the individual behaviors are picked by triggering conditions in the environment. Static priorities are not always a possibility. We made a Lego version of the Pac-Man. The 2 red robots are the ghosts. The yellow one is a remotely controlled Pac-Man. They run around the maze, and the 2 red ghosts has 2 behaviors. Stay on white in the maze between the black sides with the black white sensors and avoid if it bumps into something. everybody knows that this is the most urgent behavior when this one is running. But every now and then, when this one gets control, it backs off and out of the maze, because we're not looking at the sensors anymore. So we might solve this by looking at the sensors during the avoid behavior, or by having a switch of priorities. And this is what they do when they describe how animals switch between behaviors. We have a bunch of behavior patterns in this model of the animal. Only one of them is active at a time. It's something called motivation that determines which of the behaviors are active. If its metabolic consumption is very low in sugar in the blood, it gets hungry. And then the motivation for getting something to eat rises. If it's late night, it has a motivation for resting. If it sees an enemy, it has a motivation for running. And to model this on computers, you simply have a number of time-dependent functions that describe the motivation for the different behaviors, rising, up and down. And the behavior with the max motivation value is then the one that gets to be the active behavior. This has been used in the Mars rovers, and this is used in vacuum cleaners. This is used everywhere where robots are put out in environments that are hostile, trying to model them as animals that try to survive. The most important behavior is to get reach out for vacuum cleaners. That is, stay alive. And now to a demonstration of some of the in-course projects. Some of them choose very control-related projects, and some of them choose very embodied agent-related projects, like having a flock of robots running around. This group has decided to start with the Segway and then the Lakeway that we built during the 10-week period. Instead of the light sensor, they added a gyro sensor, because then it can also drive up and down hill of the Allison track. Then they decided, after having done this, that they need to rebuild, because small wheels are not good for balancing. Large wheels, and this one put a little up so that the weight is up here. Then they added light sensors and a distance sensor. So besides being able to balance, this is also able to avoid when something comes too close, and to follow a line if it recognizes a line. Let me try. I'll try again. Okay. Now it calibrates to know what is horizontal. Then I choose to put the avoid behavior on, and the light follower behavior, and then start it. I mean, it's oscillating a bit. This is because it's computer scientists. Engineers would have done it better, right? If I put my hand close to it, it will avoid me. I should have had a larger shaper. Let's see if it follows the, yeah. Okay. Now, there are different goals in this robot, but the most important goal is to balance, right? So the balancing behavior, the balancing behavior is the utmost priority. And if I put my hand in, it won't follow the line, but then the avoid behavior becomes the active one. Whoa! And now it tries to follow a line again. Right? You know, the system inside here is just like the system in any vacuum cleaner. Okay? With a lot of behaviors, I think there are 20 to 60 behaviors inside a vacuum cleaner. And the most important system inside that is to choose the behavior that is the most appropriate behavior at any time. Some of you have learned how to program by means of something like this, a little turtle running around on the screen drawing some silly, stupid drawings, right? How many of you have done this? I know. This is where you got the poison. Because then you try to think about things as if they are an ideal world. A virtual world where all mathematics just fit with what comes on the screen. Now, Simon Pappard's original idea, and this is the original turtle from 1969, was also to integrate understanding of the physical world into the understanding. Embedded systems into the understanding of trying to do this. Here is an early version of kids trying to control the drawing equipment. A lot of my students try this, building something like this, running around drawing. And you know, they start out with this strange attitude that the real world is ideal and mathematical and filled with logic. It's not. This is a magnet sensor. They're trying to figure out the direction where they're going because they know that the chuckle counters on the wheels are not enough to make sure that they know their position because the wheels are slipping. But this doesn't work either because there's a lot of wires underneath the floor in the lab. The magnetic field is totally random. And every time they try to do this, they try to do as if they were in a virtual world. It was only this year that a group of a group trying to recalibrate by means of some kind of sensors that measure distance to the walls every now and then. Another line is to do some robotic game. And here is a game where two autonomous robots are trying to fight each other. And it's in Danish, so I'll try to explain what's going on. So two robots, the blue one and the red one, are going to fight each other. There's a camera in the above the two robots sending information to the PC so that the PC can send information to the robots where the other robot is, because it's rather hard to find sensors so that they can figure out where the other robot is. Now they're supposed to run around and bump the other on a touch sensor sitting on its tail. And this system that they really worked on hard to give information to these two robots where the other robot is doesn't seem to work like that. This is always what's happening. They're interfering with the autonomous robots because they're not really autonomous. You see, they obviously do not know where the robot is. So somehow the picture analysis doesn't work. Or somehow the information to the robots doesn't work. But in the end of the video, you'll see that they take the two robots in their hands and make sure that they actually get points. But it takes some time for them to realize, why are they spinning? This is one of the problems with robots. It's very hard to debug the system. Come on. Hit the other. It's supposed to hit it here because here's the touch sensor. This is an example of this idea that we can get total information about the environment so that we can control it by means of all this information. X, Y, Z coordinates, angles, etc., etc. This year, some students took the idea, but now it's 4 autonomous robots running around. It's actually supposed to be the turtles from what is it? The animation world, the Ninja Turtles, the 4 Ninja Turtles. And then we have a bad robot, an evil robot, Shredder, running around trying to bump the turtles on top of them. And now the kids are supposed to control by means of this keyboard Shredder running around. And each time the Ninja Turtles get on the pizzas, they get more life and power. But when they're hit by Shredder, they lose power. And now they're supposed within 2 minutes to see if they get some points. It's still a prototype. We're exhibiting it in a museum in Horsens in 2 weeks. But as you can see, the guy is controlling this one, trying to mock them on the orange little disc. This one is eating some pizza, right? This one they found some pizza there. But they can still be beaten even there if they're eating pizza. In conclusion, I found 2 papers that I include in this presentation, because they both talk about this idea of having autonomous mobile robots in the computer science curriculum. Because all too often in the computer science curriculum, as well as FIFA said, we think about systems as if they were virtual machines or virtual worlds. There's nothing outside of the program. And there's a lot of ideas, he called them powerful ideas, you get if you think about the whole system integrated as the environment, the physics of the system and the control program. At least if you are designing embedded systems, you need to have the other two components integrated into your process. This one is Fred Martin's paper, the one that wrote this book. He has a course, or has had a course for many years, starting in 1991, a 1-month course for engineering students, trying with a robot competition. And he found that all the engineering students being taught like they do, with a lot of theory and no practice and no hands-on experience, they come with some ideal notion about what is physics, what is electronics, what is programming, what is environments. And they mess up completely. And I know this because every year I'm in charge of a number of robot competitions for school kids. They come with this idea that the robot knows what I know. That they have this view, a very egocentric view, and the students also at MIT has this. They can't see it from the robot's point of view. And information is coming through the sensors. No, it's not. It needs to be interpreted. And if you interpret it wrongly, you need to do something about it. So, if you're interested in how to develop yourself into embedded systems, and how we try to develop computer scientists into knowing about embedded systems, you might read these papers. It's very amusing to read. Thank you. Where you can buy this? In any toy shop, less than 2,000 Danish kroner.
Can it stand up from that position?
No, there's not enough power in the motors. They have tried this, really, because then they could write a program for autonomously learning how to balance. Because when they fall down, then up again and try. But they've tried with everything like touch sensors to detect when it's down and stuff like that. So it's so much easier to experiment with PID controllers with this one, because it's still there when you miss it, right? But this one is not easy. There's the leJOS Java system. If you have this robotic kit available, it's really very nice. It's stable, it's well documented, and it's very nice to use. And since the students know Java when they come, programming is not an issue. It's learning about this sensor actuator stuff. And some of them build their own sensors because it's very easy also to do electronics because it's open source from Lego how the different things are connected to the NXT. So you can get recipes everywhere on the net to build new sensors and build new actuators, etc.